All right, so this section of chemical reactions is going to focus on oxidation-reduction reactions. These are commonly called redox reactions, re for reduction, ox for oxidation. And these are different from the precipitation and acid-base reactions that we've looked at so far, as well as the gas-producing reactions, because they result in a transfer of electrons. You don't just have ions being exchanged. You have to have something losing electrons and you have to have something gaining electrons. So for that to take place, both oxidation and reduction have to occur. Oxidation is going to take place when there is a loss of electrons. The element that is undergoing this oxidation process, because they are losing negative charges, will become more positive. They'll increase in oxidation number. And whatever contains that particular element acts as the reducing agent. It's able to facilitate the reduction process because it gives a place for electrons, it gives up electrons that then can be gained in reduction. So what is undergoing oxidation and what is acting as the reducing agent will both contain the same element. Oxidation is just the element. The reducing agent is the ion or molecule that contains that particular element, and they both have to be on the reactant side. Reduction is going to be the opposite of oxidation. It's where you have a gain of electrons, and because you're gaining negative particles, you decrease in oxidation number. If you are undergoing reduction, you are acting as the oxidizing agent. I don't know why I said reducing agent there. I'm really sorry. All right, so this section is going to focus on redox reactions, or also known as oxidation-reduction reactions. These are different from the precipitation and the acid-base and the gas-producing reactions we've seen so far because electrons are physically transferred between the substances, and that's what's acting as the driving force and allowing this reaction to occur. You have to have both processes occur in the same reaction. You can't just have oxidation occur. You can't just have reduction occur. They both have to take place. Something has to lose electrons and something has to gain those electrons. Oxidation is going to be known as the loss of electrons. When you are losing your electrons because you're becoming more positively charged, since you're losing those negative particles, you increase your oxidation number. Whatever contains the element undergoing oxidation acts as the reducing agent. It's able to facilitate the reduction process by providing it with a source of electrons that will allow it to gain them. The reducing agent is not just the element alone undergoing oxidation unless it's just found as an element by itself. It's whatever molecule or ion contains that particular element, and they have to be on the reactant side. Reduction is the opposite of oxidation. Often we refer to these two as oil rig or Leo the line goes Gur. Oil rig is for oxidation is loss, reduction is gain. Leo the line goes Gur, loss of electrons is oxidation, gain of electrons is reduction. When you're undergoing reduction, because you are gaining negatively charged electrons, your oxidation number decreases, and you are able to act as the oxidizing agent. You facilitate oxidation because you give a place for those electrons to go when something is undergoing oxidation. And just like with the reducing agent, the oxidizing agent contains the element undergoing reduction, which could just be the same as what's being reduced, or it is the molecular ion that contains that particular element. And again, it has to be on the reactant side of the equation. So we can use oxidation numbers, which is a fancy way to describe charge, to determine whether a redox reaction has occurred. And with our ionic compounds, it's pretty straightforward. With the moleculars, we have to think about it a little bit more in terms of electronegativity. So we have some rules that we always follow to determine oxidation numbers, and they're pretty straightforward. When you have an element that's by itself, and that's the only element that's there, it's monatomic, it has an oxidation number of 0. If it's a molecule like F2 or P4, they too would have oxidation numbers of 0. Monatomic ions, ones from the periodic table, will have an oxidation number that is equivalent to their ions charged. And if we start getting into the molecular substances, electronegativity is going to have a key determining factor as to what oxidation number elements that make up compounds will have. Fluorine will always be -1. It's always going to win that battle. Oxygen will be -2 unless it happens to be paired with fluorine, or if there are two oxygens being used to make up a peroxide compound. And in that case, it would be -1. Chlorine, bromine, and iodine are also pretty high up the ladder. They're always going to have oxidation numbers of -1 unless they're paired with fluorine or oxygen. So the further down the list, the ones above it basically can outlast the ones below. Hydrogen will always have an oxidation number of +1, and the only other time you're going to see hydrogen be in a compound would be with a metal, like with batteries, and if it's with a metal, then it would have an oxidation number of -1. If you have a neutral molecule, all of the oxidation numbers have to add up to 0, and if you happen to have an ion, all the oxidation numbers have to add up to that ion's charge. So the elements that aren't listed here, you're going to have to use this information to help you determine what their particular oxidation states or oxidation numbers are. So here we have SF6, and we know from our rules that fluorine always is going to be -1, and we have 6 of those present. And since the overall charge oxidation state of this molecule is 0, we would need 6 -1s to be balanced out with sulfur's oxidation number. So sulfur, if you were going to solve this algebraically, would have to have an oxidation state of +6. You don't have to show the algebra. That's just to give you a way to relate the two, that sulfur's oxidation number and the 6 fluorine oxidation numbers need to equal the charge of the molecule, which in this case is 0. In letter B, we have an element by itself. I don't care if it's monatomic, diatomic, tetraatomic. If it's by itself and there's no charge associated with it, its oxidation number is 0. In letter C, we've got 3 different elements, and there's only 2 of these 3 that we talked about on the previous slide. We know that ions from the periodic table, this is an ionic compound because we've got magnesium with a polyatomic P2O7. Magnesium is always going to be +2. And we also know that O is -2 unless it's with fluorine or a part of a peroxide, and that is not the case here. So we know those 2 components of our compound, and we know the overall charge needs to add up to 0. So if we have 2 +2s and we have 7 -2s, we have a +4 and a -14, which would give us a charge of -10 or an oxidation state of -10, making up the magnesium and oxygen components. So the 2 phosphoruses need to balance out that -10, and to do that, each would need to be +5. +10 and -10 would add up to 0. Got 2 more for you here, SiH4. We never talked about silicon, but we did talk about hydrogen. We said as long as it is not paired with a metal, it's always going to be +1. Silicon is a metalloid. So we have hydrogen being +1. We happen to have 4 of those present. So silicon needs to balance out the 4 +1s that hydrogen contributes since the overall molecule has a charge of 0. The silicon would need to be -4. Finally, in our last example, we do have an ion this time. We've got nitrogen and 3 oxygens. We never talked about nitrogen having a specific oxidation state, but we did say that oxygen would be -2 unless it's paired with fluorine or is part of a peroxide, neither of which applies here. So the 3 -2s plus nitrogens need to add up to the charge of this ion, which happens to be -1. So the nitrogen's oxidation number in this particular ion would have a charge of +5. So this information can help us determine whether we have redox reactions taking place, and that's what happened with your precipitation lab with the reaction between copper and iodine. So if I take a look at this particular equation, it's a net ionic equation. So you have copper and silver ions making silver and copper ions. We know that copper, being a neutral element, is always going to have an oxidation number of 0. But silver, being an ion from the periodic table, that's going to be its charge +1. Over on the right side of the equation, we have silver without a charge, so that's a neutral element, an oxidation number of 0. And copper is now in its ion form. It has a charge of +2, so its oxidation number is +2. So if I look from the reactant side to the product side, I see that this definitely is an oxidation-reduction reaction. Copper increased in oxidation number, silver decreased in oxidation number. So because copper increased in oxidation number, it was being oxidized. And because copper is by itself on the reactant side of the equation, we'll talk about the agents in a second. Sorry, I wasn't sure if that was coming up now or not. Silver went from +1 to 0, so it was decreasing and therefore being reduced. If we look at our oxidizing agents and reducing agents, copper was oxidized. It was an atom by itself, so it's also acting as the reducing agent. Silver was not by itself initially. Silver was an ion, a +1, so the silver ions were acting as the oxidizing reagent and oxidizing agent in this particular example. So our next example, we've got HCl and NH3 making NH4Cl. If you remember, I said that acid-base reactions are not going to follow the redox rules, because remember, the ions switch places, or in the case of a weak base, they just come together to form a salt. So this one then should not be a redox reaction, but I do want to go through and show you why that is the case. We know that chlorine is always going to be -1 unless it's paired with fluorine or oxygen, not the case. We also know that hydrogen is always going to be +1 unless it's paired with a metal, also not the case. HCl is balanced, +1 and -1 give me an overall oxidation state of 0, but I need to take care of nitrogen in both of the remaining compounds. If I have 3 hydrogens in NH3 that are +1, the nitrogen that's making up that molecule would need to be -3 to balance it out and make it neutral. NH4Cl also needs to be neutral. We have 4 pluses with the H4, and we have a -1 with the chlorine. The 4 and -1 gives me +3. I need to have nitrogen be -3 to balance that out. So if we look from left to right, we see that hydrogen stayed +1, chlorine stayed -1, and nitrogen stayed -3. So that is why this acid-base reaction is not going to be classified also as a redox reaction. Your precipitation reactions, where the ions switch places, your acid-base reactions, where acids react with bases, those are never going to be redox reactions in the ways that we presented them so far, because all they do is result in ions switching sides. In letter C, we have silicon tetrachloride and magnesium makes magnesium chloride and silicon. I believe this is our last example. So if we look at what we have been given, we can tell that chlorine is always going to be -1. Sorry, we're doing them one at a time. All right, so silicon's -1. Sorry, chlorine is -1. We've got 4 -1, so silicon would need to be +4 to balance it out. Magnesium is by itself, so it is not an ion. It would have to be neutral with an oxidation number of 0. In magnesium chloride, magnesium is always going to be +2 because it's a metal from the periodic table, a monatomic ion, and that's fine. Chlorine is always going to be -1, and together, 2 -1s and +2 add up to an oxidation number of 0 for this compound. And then we have silicon by itself on the product side. Anytime you have an element by itself without a charge, its oxidation number is 0. So in this particular example, chlorine did not change oxidation states, but silicon did. It went from +4 to 0, and magnesium did. It went from 0 to +2. So this is indeed a redox reaction. Silicon going from +4 to 0 decreased in oxidation number, so it was being reduced. Magnesium going from 0 to +2 was increasing in oxidation number, so it was being oxidized. Si was part of SiCl4, so SiCl4 is acting as my oxidizing agent, and Mg was by itself to begin with, so it was just acting alone as the reducing agent.